university in Freiberg. We call it Bergakademie Freiberg. I'm not sure if there's a good English translation to that. So Berg means mountain. So it's a university in Germany which is handling the processing of minerals, blasting of rocks, and so on. So it has a long tradition in mining. So it's a mining university, maybe it's a good translation. And Holger, in this institute, he is looking for more efficient machines for processing raw materials. But not only on the machine level, he is also really looking into the micro scale. That means how a material behaves in such a machine and what is the reason that materials behave different. And also regarding selective comminution and so on. So that's, I think, the bringing together the machine behavior with the material behavior on the micro scale. That's what he is looking for. And Holger has a lot of experience also from industry. So he was building and selling machines all over the world before he comes to the university. That is a normal way in Germany, at least, that after your PhD, you go into the industry for, let's say, 5 or 10 years, 5 years at least, but probably more often 10 years about. And then you are coming back. And that's, I think, a great experience that you have then on, let's say, real machines and real making money with such products. And this experience has Holger, and now he is with this experience, and I think the knowledge of him and his group, he is doing a fantastic research in this field, and I think we will get today some results of it. And the title of his speech is Aspects of Particle Size Distribution and Material Characteristics in Confined Bed Comminution. So Holger, please go.
Sure. Thank you very much, Arno, for this kind introduction. When I was approached with regards to this today's seminar, I was thinking about a suitable topic, and I thought the confined bed comminution is still a topic which it's been around now for some 30 years or so, but still a lot of open questions, and the technology is still on the way to make its inroad into new fields of technology and application, particularly in the ore processing. And there is a number of questions, particularly related to this, I would like to tackle and at least also to present towards the end some of the more recent research aspects and results here at our institute. So the presentation will be split into the 4 parts. The first one will be an introduction to confined bed comminution. Then there will be some basic ideas with regard to the application. And then I will present in the third topic the particle size and certain strength relationships into it, and the coming up with a very brief conclusion. So to start with a confined bed comminution, first what we are talking about here, I always like to start with a scheme where we see, or where to show where we are. Essentially, we split the comminution machines into machines with tools and without tools. And today we are mainly referring to the mills with direct driven tools, particularly the roller mills or the high pressure roller mills, the VRMs. So this is what will be the background of our today's talk here, of my today's talk. If you look into this scheme, we have here shown the specific energy consumption over the particle size of the feed material and the product material, and this is split here with a number of mills. The scheme is essentially not new. It's being done with Hubble also many years ago, But when I saw it, I found the interesting point is this arrow here. You can see very nicely what is known from our bond scheme, that the finer you are getting with your particle comminution, and this is certainly reflected with certain technologies behind, then the higher the energy consumption will be. Ending up with the jet mills or the stirred media mills here in the upper areas. And for the confined bed comminution, essentially we are talking here about mainly the roller mills. Here is two different types of roller mills indicated, even the vertical roller mills with balls actually and with rollers. This is the two machines, and if you see, we are just close to the autogeneous mills. This is the number H, and we see that that is, of course, depending on the particle size we want to achieve and we want to deal with. And on the other side, of course, we see already that we are with this confined bed comminution, we are tackling particles which are bigger than the normal crushers, which are ending up here with roller mill, with the roller crushers and with the rod mills here, which are phased out quite a bit in the mining, the rod mills, replaced by the sag mills and the egg mills. And now we see a process where the HPGRs and potentially the VRMs making their way into the industry. And both VRM and the HPGR, this is in the industrial size, the machines which are working on the basis of confined bed comminution. And still there's small differences between the two mills. Despite we have this main, the compression as a main load, we see differences in the details if you're coming to the operation of these machines. So the VRM is one machine, the other machine is the HPGRs. Of course, the left one here is not in our laboratory, would be too big. This one is the machine in our lab, so still with a diameter of about 1 meter. So what is the advantage of using this type of machines? The HPGRs were introduced with Schönert somewhere in the 1980s, late 1980s. And there have been a lot of publication, investigation on the application of these machines. Initially in the 90s, there was a lot about their applications in leaching processes and the advantages mainly with regards to these latent cracks here nicely shown in this picture from Van der Meer in a paper. And with these latent cracks, there could be shown that you have an improvement in recovery if you are using these HPGRs in connection with leaching systems. So that is now in some areas, these machines are used, but here we are not so much looking at the confined bed comminution as such as what we want to see now. Because for the leaching systems, usually you are not focusing too much on the production of too much fines. If the fines content would be too high, then your permeability of the leach bed would be too low, and so which would not be good for the process. So the advantages of the confined bed comminution, one of the advantages is the reduction in energy consumption, specific energy consumption. This is a picture which was derived or published in a brochure of Comminution for clinker grinding. It shows quite nicely the advantages in energy consumption, replacing the at that time dominant ball mills by HPGR. And you can see at that time a typical ball mill in cement industry was driven with a 5,000 kilowatt motor. If you would replace it at least in a hybrid grinding, so-called hybrid grinding or semi-finished grinding, you could reduce the total power consumption. This is the yellow column here from the left. So you're here, if you take the 100% ball mill, the 5,000 kilometers 100%, then with a hybrid grinding, you would end up at some 80-something percent energy. Semi-finished grinding at 60 or 70%, so you have 30% savings, and with finished grinding, you would end up with close to 40% energy savings. Of course, and this has to be, this is not shown in this brochure, as sometimes quite common. The energy consumption here for the classification is not shown here. You need to have, for the confined bed comminution, you have to regrind the material a few times. So usually with every step, you grind maybe about 20% of the material to the final particle size, which means you have to pass the mill with the material in the range of about 4 to maybe up to 10 times in the worst case, if you have a very competent rock or ore. Usually it's about 5 times that you have to pass the material, so you have to lift the material again, and you have to classify the material, which is consuming part of this energy savings, which is shown here. But, and I think that is proven, and for sure, there is a nice presentation from application from Freeport, where HPGR was added to release the ball mills, and they reported an energy savings in the range of 10% over 9 to 10%, which is still significant looking at the high energy consumption. So I think it's still worthwhile to talk about, but for sure we are not talking about 30 or 40% in the total. So we see the HPGRs made their pass into the ore industry already. So we have HPGR applications there, schemes like this one. And this scheme already shows me one of the, or gives me the opportunity to reflect a little bit on the application. We have seen that the HPGR in the previous picture is used for finish grinding. This is, in principle, this is possible, but the HPGR only produces, pretty much only produces compressive forces. And with compressive forces, it's very difficult and then again, energy consuming to go to very fine grinding. So if we go to particle sizes way below 40, 50 microns, then the HPGR with just, mainly just compression loads, maybe not that efficient anymore. That's most probably also the case why you use here the ball mill in this gold application. And in cement grinding, clinker grinding, there's other reasons with the particle size distributions of the cement, which is another important factor there in the cement industry. But also in cement, usually you find HPGRs in combination with the ball mill than as for the finish grinding. So the focus is essentially to replace the egg mills and the sack mills. The egg mills and sack mills are the workhorses in the ore industry nowadays. They are nice because you just have one big piece of equipment which you have to control, which you have to maintain, and that big piece of equipment is doing all the work. In some cases, as for instance in El Salvador in Chile, you just have this one mill in the whole operation. So that mill does the whole processing from the rock size of 300, 400 millimeters to the flotation size with recirculation of the material, etc. Is it efficient? Certainly not. But on the overall operation, yeah, it could be, there could be some arguments in favor of such a solution. So the typical solution nowadays is a combination of sack mills and ball mills. And the disadvantages is like with all toppling mills, you have a very high specific energy consumption. you have a rather high water consumption, which is also coming more and more important topic. So that is why people are thinking about alternatives. One alternative, another alternative might become in the future the VRMs, the vertical roller mills. In theory, you might replace that whole area of a processing circuit, of a beneficiation circuit. In theory, you might replace that whole area with vertical roller mills. Actually, not with one, because the capacity of that one mill would not be sufficient to meet the capacity of one SAG mill. That has to be said. And also the feed material size, 150 millimeters, is smaller than the SAG mill, so you might have another crusher step, or you might need another crusher step in between. But then you would come to a dry grinding, you would come to a more energy efficient grinding. So the idea behind seems to be appealing, at least. So the size here, the feed size is 150 millimeters, and you might grind down to 20 microns, something like this. When you see already there's a difference in size reduction between the HPGRs and the VRMs, and this can be explained by the crushing principle. So we have with the VRM, we have in most of the cases we have a certain share also, and the share is good for final grinding, of course also for increased wear. So that would be the interesting area to discuss. Another advantage which I didn't mention, and that could be even more appealing to the industry than the energy and water savings, could be the increased recovery. Recovery still is and will be most probably the main driver for the mining industry. And when they see an increased recovery, all of a sudden you catch the attention of the mining people. So we did some tests with iron ore grinding a while ago already. We did the tests in with materials from Kiruna or from LKB mainly. And we did also tests with tungsten grinding in Mittersill. So what you can see here in that scheme is we have the liberation ratio in the existing ball mill circuits, and you can see the red triangular here, that is the point which we reached with the vertical roller mill, and you can see we reached full liberation at coarser stage with this mill, which means at the very end energy savings for the grinding and reduced losses for the flotation. So this is one step. And the other thing which we could also show with this ores which we investigated there, but this is another scheme I have found here for nickel recovery. You can also show an increased recovery by flotation if you go with dry grinding. Dry grinding obviously has advantages since the surfaces of the particles are not spoiled by the slurry so much, and therefore you can see increased recoveries. Another advantages, or a point which speaks in favor of the dry grinding, here in this particular case 25% reagent savings was reported, or same recovery in a sort of time, which might also be interesting. So confined bed comminution is unique due to energy savings, maybe up to 30%. In practice, I would go to maybe 10–15%. Still interesting. Water savings, throughput, low wear rates, low energy consumption, increased recovery. So some basic ideas. What are we talking about? The main thing is in confined bed comminution is compression. But in certain cases, or to a certain extent, we always have sharing. We have way more sharing with VRMs than with HPGRs. But in our laboratory, we could also see after we had removed the or the material layer which was pressed in between the studs, which is the so-called autogenous wear protection, we could see underneath very clear signs that this autogenous material layer under pressure is even pushed and sliding over the surface, which was quite interesting because we found clear signs of wear underneath the surface. And with these marks, we could find underneath this layer and on the surface of the roller, between the studs, you could see even the directions in which way the material was flowing. You could see very clearly that in the center of the roller, the material was flowing in the direction of the material in the vertical direction, while towards the sides of the roller, you could very clearly see the indications of the material being squeezed to the sides, and you had a clear wear direction in the sides. So which means you also have a shear load in the material in the HPGR, not as much, of course, as in the VRM. In the VRM, you have differential speed under the roller, underneath the roller. So you have the rotating table, not shown here, and you have your roller here, section shown here. So in the contact area between the roller and the rotating at the table, we have a speed pattern like this one. So which means if you have adjusted the speed of the roller in the center to the speed of the table, so that you have a zero relative speed between the two at this point. Then on the outer side, due to the increased diameter of the roller here, the conical roller, you have a higher speed of the roller compared to the table, while in the inner side, with the roller, with the lower diameter of the roller, you have a lower speed. So which means you have in the gap, you have a shear between the roller and the table, which is helping you to produce finer material compared to the HPGR. Of course, to the expense that you have additional wear in these machines. So with this particular roller design here, with these conical rollers, you have the chance to adjust this speed at a certain point. You may even reach the area that you have no relative speed. So that is possible when the central line hits the central axis of the table at this point in particular. Then it works. You have no relative speed. For all crowned type rollers, you have even more complicated schemes here. Particularly on the sides, you have much more shear there, which is a disadvantage if you have very abrasive material. But if you go for the original application of vertical roller mills, which was the coal grinding, in coal grinding, you wanted to achieve very fine material with least effort. And in coal grinding, you have material which is not very abrasive. So for coal grinding, the grounded rollers are certainly preferable compared to this flat or conical rollers or even cylindric rollers, which are nowadays also in the market. So the relative speed here makes a difference, makes a major difference between the HPGR and the VRM. So that needs to be kept in mind considering the difference of the two mills. Coming to the principle of confined bed comminution, essentially we see here the material is consisting of a number of layers. According to Schöner, it should be at least 5 to 6 times the diameter of the maximum particle. And you have the so-called hydrostatic status of comminution, which means all particles are stressed the same way. And preferably talking about selective comminution, if desired, we see that the weaker particles are breaking earlier than the stronger particles. And then, if that works nicely, according to theory, you just could use your screening or air separation to get the finer particles out, and you get a pre-concentrate. so much about the theory. So you have the multiple contact points, you have the fluid-like all-over stressing of the particles, and you have a less overgrinding in the material. I skip this one. Coming to the phases of confined bed comminution, we have the repositioning of the particles at low pressures, then we have the plastic deformation of the particles in the next step, and only after that point we come to the final step of comminution of the particles. This has to be kept in mind in designing also the machines. For instance, when I saw that new design, this HRC with this arch frame, which was even in the advertisement, it was advertised that skewing of the rolls is not possible there. I found these people might not have understood the really operation of a confined bed system, because there you want to have the same pressure on all the particles. If you avoid the skewing, and if you have one big particle, that big particle gets the full pressure of the rolls, and all the other particles get nothing, so in the worst case. So that's why at least a certain skewing should be allowed to achieve a good confined bed comminution. So in the principle itself, I think I should not come into too much details here. The principle itself about this arch frame is not new. We have seen this for double roll crushers in the old textbooks. It has certain advantages, no doubt about this. For the operation of the machine, it has also advantages. But in particular, if it comes to the confined bed, I have my doubts whether this is the right way of producing a confined bed in between the rollers. So the motion patterns of the movable roller here are shown. This is a common thing. And the product of this confined bed comminution is then usually, or in many cases at least, it's type of flakes. Depending on the material you are dealing with the ores, you don't have the flakes regularly or too often. If you're talking about applications of these mills in limestone grinding also, then you regularly have these types of flakes. The question is, do you have these flakes only in fine grinding? So the topic today is confined bed comminution. And to produce those flakes, you end up in very high peak loads. So you think back about the steps of comminution, and at the very end, once you have achieved the full compression of the material, and the particles start supporting each other, and then you have more elastic deformation than really comminution. So at a certain point, and this is usually said in the literature, 80% solids, which in the space in the crushing gap, then you don't achieve more comminution. And if you think about what happens then, you find comminution or confined bed comminution happens in many cases where you wouldn't even think about it. So these nice agglomerates here of powdery material, in this case it was limestone, they were not produced on an HPGR, they were produced on a flat-face double roll crusher. So let me see whether I can just jump to a small movie. We tested it before, I'm not quite sure. I can jump to this one now. So can you see this?
Yes, we can.
Oh, perfect. So you see, we are talking about a flat-face double roll crusher. We have just single particle comminution here. As you can see, this particle has a diameter or a maximum length of about 16, 18 millimeters. So it has essentially a lot of space to escape there. So you can see there's no other particles preventing it from moving. And still, with these single particles feeding to this flat-face double roll crusher, of course, with a very narrow gap, you see that at a certain point, the material has not enough time to escape anymore. And then in the center, you're producing these flakes and you're producing extreme high peak loads. And this would essentially, let's stop this one here, jump back to the other presentation again. So we produced these flakes here with a material at a speed, a limestone fraction 20 millimeters here, speed of the surface 3 meters per second at a gap of 0.8 millimeters, which was pretty fine. The focus there was what is the relationship between diameter and is there any influence of the material? We use also other materials. Is there any influence of the material, how it is taken into the double roll crusher? So you see, and we did also some other single particle comminution tests, and I'm coming now closer to our topic, the piston die test. And we did some investigations with the piston die here. Also earlier, also with different materials, with quartz, with granite, with limestone. And what you can see here is a particle which had originally the size of 300 millimeters. So reduction ratio here was the original height, as mentioned, 300 millimeters. We pressed it to a gap of 80 millimeters. And you can see there was enough space on the outside, so the material could have escaped, but it did not, because due to friction, due to the structure of the material. So essentially, the structure of the material was looking like this, and inside the material, you had already a particle bed which was formed, and you could see on the particle size distribution, you could see that there was a particle bed because you produced a lot of fines in the material, which is important to understand for many of the comminution processes, particularly for the coarse crushing. People are not even thinking about confined bed comminution, and still they are into this. So in this single particle comminution, we achieved already the confined bed situation, or this caking already at reduction ratios of less than 3.5%. Now think about what we are talking in many of the primary crushers, like jaw crushers, cone crushers, or others. We are at reduction ratios of 5. Of course, not in one step, and this is also an important point, whether you achieve a certain reduction radius in one pass or in several passes. So this is another picture here. The diameter of the pot is about 1 meter here in this case. You see the original particles here. In this case, dolomite, the gap 80 millimeters, and you could see the larger lumps were falling aside, of course, but inside you always had the formation of this caking and of this particle bed. You could see this, and we did some comparable tests with dolomite with different particle sizes, feed sizes, and different presses actually, also 130 millimeters, 12 millimeters, and 0.8 millimeters. That was all piston die tests here. And we compared the results with the double roll crusher test and with the jaw crusher test at different feed particle sizes also. And then we looked for the self-similarity, essentially using cumulative or normalized cumulative particle size distribution curves. And what you can see here is these bunch of curves. This is all the curves from the piston die test, various sizes, pretty much falling onto each other, including also the curve of the double roll crusher. This is the one with the black squares here. While the curve of the jaw crusher is significantly different. This is much steeper here. And the explanation is very simple. If you look at the operation of double roll crusher, in particular the flat face, but this is same for all double roll crushers. For double roll crushers, your comminution appears in one pass. So the material is being drawn in, and then it's comminuted, and then it falls out. In the jaw crusher, the material is comminuted in steps. You may end up also with a reduction ratio of 5 or 6, but then you have you release the material. It has time to reposition itself, and you might even have a classifying effect with some fine materials passing the crushing chamber earlier. So that is why with a jaw crusher you typically would see a steeper particle size distribution curve than with a double roll crusher here, as what you can see here. And another important another thing when I had to remember when I was reminded to this point is we had a case when we were called by an operator of a crushing plant, a fully mobile crushing plant, actually here in Germany. And he had a problem with his crushing plant system because it was terribly shaking, and essentially already the handrails were falling off in a pretty new machine. They were just collapsing. And he asked us for our advice, and we inspected the machine. And when I saw into the crushing gap here, I found the crusher has been operating for about a year by then. The material being not very abrasive. It's like a limestone, quite competent, but not very abrasive. And what you can see here is a crushing gap. So now think about where could the material can escape there. So it was very clearly, and the wear here, the wear on the teeth was not at the tip of the teeth. The wear was on the rear side, on the back side of the teeth. You can see here very nicely, shiny parts on the other side as well. So essentially the material was rather squeezed here, and the material didn't have the chance to escape, and that's why you produced extraordinary forces on the machine. And these forces led to the oscillations which finally brought several parts there to fall into the steel structure to fall apart, because simply the forces here were too high. This is again a graph drawn from our flat face double roll crusher here, which we've seen in the movie, which is equipped with a force measuring device over the roll angle. And what we could see there was a pretty similar picture to what you would find with the HPGRs. Here we have the angle 0, which is just above or the connection line between the two roll centers, and just about 2 or 2.5 degrees on top of it, you have the maximum force acting on the rollers when crushing a lump there. So which is a curve which is very well known from HPGRs, very similar. And we found it confirmed even with a double roll crusher. So if you don't give the material enough space to escape or to flow onto sides, and you remember single particle comminution, we are usually talking about a filling ratio of 15% solids in the crushing gap. But even if the average 15% is achieved, if you don't allow every single particle this 15% solid ratio only, then you might create substantially high forces. And not only the high forces, coming along with these forces is also the production of a lot of fines. And in many cases, you are not interested in the fines. In this case of the real crusher I've shown before, the people wanted to have this fine material. That's why they closed the gap too much, perhaps. But in many cases, you don't want to have the fine material, and so you should avoid also these high force peaks. So coming to the particle size strength relationship, Of course, we always start with the mineral processing as a black box model with the material feed material coming in, material product coming out, energy in, signals out. We usually then assess the parameters influencing a comminution process, which is here a type of a more general comminution process. So we have material parameters, which we need to assess. We have certain machine parameters we need to assess, and we have system parameters, which is essentially the combination of material, machine, energy, and signal. So if you continue with the material parameters, you have certain feed material parameters, and you have product parameters, which all belong to the material parameters: feed size, PSD, mode, mechanical characteristics, etc. Product parameters usually is product particle size distribution, shape, maybe an issue, etc. Then the machine parameters, that is split again into design, into material parameters, into operation parameters. So design could be crushing chamber, inclination, size, etc. Then material parameters could be the wear parts, the manganese, or the young modulus of certain components. And the operation parameters are also important, like filling degree of the crushing chamber, etc. System parameters are often forgotten, but they are also influencing, like the stored energy in the system, the mass of inertia, etc. And you have certain target parameters, could be specific energy consumption, selectivity, and comminution. So talking about confined bed comminution, we have many influences here. And so it could be the bed dimensions, which is for, at least for the ideal confined particle bed, is defined by Schönert and others. Then the particle size distribution, the packing density could be an important point, the particle strength, mineral composition, etc. We have, yeah, this is just an ongoing test. I just was looking for some nice pictures here. That is a slag which we are investigating, a manganese slag, which we are investigating just at the moment for the TU project, for the Greenie project where we are in. And we try to recover the manganese in there. Influences on the confined bed comminution have been investigated quite intensively already in the past. So one of the influences which is important to understand is the particle shape and the packing density. There's not so many people looking at the particle shape in the comminution process, at least in the confined bed comminution. The packing density is certainly clear to everybody that the packing density has an influence. But we have to start earlier. The particle shape has an influence on the packing density. And so the particle shape has an impact on the confined bed comminution. What we could see here, this is figures according to an old publication of Fuller. Fuller was investigating similar effects for the cement industry. We found it quite worthwhile to use this Fuller equation also for calculating the or considering the particle shape influence on the packing density, and then reflect then on the comminution process. Another important aspect which was investigated already is the different strengths of the particles. I think that is one of the key publications in this field I'm quite often referring to, from Abu Zaid and Fürstenau in 2009, published. They used limestone and quartz, same size as you can see here, or almost same size, 160 microns F50, and limestone 190 microns. And he was investigating how the comminution occurs. And here we see in this shape the reduction ratio of the different particles, of the different fractions under a certain mixture status. What we could see here is pretty nicely that in case you are crushing the pure limestone or the pure quartz, you have these blue curves here. And the quartz or the angle of the blue curves is pretty similar, the inclination angle. So if you have the pure material just for the limestone, you need a little more, or you consume more energy, and your reduction ratio will also be higher, or at the same energy consumption, your reduction ratio will be higher, put it this way. The big jump comes if you put just 10% of the quartz into the mixture. So you have a mixture of 10% quartz and 90% limestone. Then all of a sudden the picture changes. With 10% quartz, your quartz curve remains horizontal, so which means the quartz is essentially not broken at all. You see no major size reduction, while your limestone curve is getting steeper. So we found this quite interesting, particularly if you are looking at future applications of confined bed comminutions for ore grinding and selective grinding in ores. The point here is we have the same sizes. So at least at the beginning, of course, afterwards, the limestone is crushed further, so we end up with finer limestone fractions and with the quartz fractions. But in real life, the picture is different. So in real life, we have another influence. Not only the particle strength itself is a function of the particle size. It's not only a function of material, but also of the particle size. That's why the typical comminution test for the UCS determination, for instance, they have all very nicely designed and precisely defined particle sizes, because you define a certain strength of material just depending or just for a certain size of the test particle. So if you see here also in the own publication of Schöner, they investigated the influence of particle size from glass beads, where you could assume a very homogeneous material, same material characteristics. And you can see for these glass beads, of course, the finer glass beads, finer diameter up to whatever 8-9 microns, the glass beads are much higher in strength, breakage strength, compared to the coarser particles. And this is, of course, an effect which needs to be considered. If we compare same size particles, quartz and limestone, it's very clear that the particle is, the limestone is crushing further than the quartz. But what happens if you have large quartz particles in combination with small limestone particles? Yeah, so this is another point, another investigation also from accompanied by Schöner. When again, glass spheres were investigated, mixtures of glass spheres of different sizes, and here already you can see an influence of the percentage of glass spheres here, of the indicated here as 1 millimeter glass spheres. You have, let's say you start here at the beginning at 10% of the glass spheres and different pressures. With 10% of the finer glass spheres, the specific energy consumption is reducing. But then the higher your percentage of glass spheres is getting, the glass spheres of the finer size, the more the influence is of the larger strength of these finer particles is seen here. On the other side, and this curve is also interesting, particularly if you're thinking about selective comminution, we have in the number of spheres here, the 2 millimeter spheres, if we use a certain energy at a certain energy level, of course, if you have no fine spheres, you have 80% of the 2 millimeter spheres broken. So we add 10% of the fine spheres. Still, we are close to this one because the fine spheres fit somewhere in between. And then we increase the number of fine spheres, and we see that the coarser particles are not broken anymore, or to a lesser extent are broken. This is very typical to what we have seen in the theory, that the coarser particles are supported by the finer particles during compaction in the confined bed comminution. So we investigated, this is the explanation behind. We have for the coarse particles, you have very reduced or a limited number of contact points. The forces are larger, resulting in a increased comminution. While if you have many contacts, many fine contacts, the large particle is protected here. So the forces are lower. So influences of varying particle size for identical materials were investigated. The influence of varying material strengths on confined bed comminution was investigated, but the question of the combination of both has not been investigated yet. And insofar, that was a topic we wanted to learn more about. And essentially, the approach was that we looked at two materials and looked, this is the typical whatever bond curve, or what you call it, strength versus diameter, the two materials, and we looked at what sizes the two materials would exhibit the same strength of the material. So we did it. We started with the tests with a combination of glass beads and corundum beads. With a piston die test, so you see the variety of glass beads. We investigated the material quite extensively. 1.5 millimeter glass beads, 3 millimeter glass beads, and 7 millimeter glass beads. We ended up with the breakage strength of the material and the relative breakage strength here, which was the percentage of particles broken then, and at a certain load. And you could see that particles in the range between 1.5 and 3 millimeters, they are in the range where the 1.5 parameters are closer to the breakage strength of the aluminum oxide. So that's why we use 1.5 millimeters glass particles in comparison to the 7 millimeters aluminum oxide particles. So the strength of the materials is, breakage strength is shown here. And we repeated the tests of the similar approach with natural material, with quartzite and limestone, to have also a comparison to the old Fürstenau investigations. So we used here a quartzite, also in the range of narrow fractionized, 7.1 to 8 millimeters, and the limestone in various particle sizes, 5.6 to 8 millimeters and 1 to 1.4 millimeters. Here, the 1 to 1.4 millimeters exhibited very similar strengths compared to this quartzite, 7 to 8 millimeters, slightly less than the 6.8 megapascal. So, and we did the following test program. We had so 7 millimeter particle, then we used it with different glass beads, corundum versus glass beads, and the quartzite versus limestone in the different mixtures here, similar to what we have seen with Fürstenau. The test was done here on this piston die test rig, which we had seen earlier already, at least the die was in the photo. So the velocity was fixed, the compression velocity. The initial confined bed height was 100 millimeters. The die diameter in this case was chosen to use the 160 millimeters diameter. The typical figures for investigating or verifying the test that was here for the glass beads. We did the typical tests for the various glass beads, and obviously the final glass beads here consumed the most of the energy. That is the blue curve here. So that is just for comparison. Important was to develop a figure, a value, how to evaluate or to quantify this selectivity or this comminution result. And we used again this so-called selectivity, which was used and derived in the work by Hesse earlier for the selective comminution. Here essentially we used it in a different way for certain reasons. I don't have the time now to go into too much detail for the background on this. So essentially we defined the selectivity as the space between the two curves here, and or the area between the two curves. And the selective comminution value is then the difference between the two curves of the feed product and of the feed end of the product. So essentially, if you have a mixture of two materials like quartz and limestone, so you might have a slightly different curves of the feed materials already. So there could be these two curves here, and we see the selectivity between the two already as a starting point. And then we see how this selectivity might have changed in the comminution process. So we use that space in between the new curves here, between again the class 1 and class 2. We do the differences, we take the difference between the two curves, and the result could be negative, could be positive. Essentially, also important to know that the results can be negative, which just means that the particle which was called at the beginning, a negative figure would show that it's finer after the comminution process. So, and these are the results which we have achieved with this glass beads. To start first with the glass beads 7 millimeters compared to the corundum fraction also being 7 millimeters in the different mixtures, and you can clearly see that in the initial case we have a small number of glass beads here, so the number of broken glass beads is smaller, while in the case of about 50% glass beads and corundum beads, then the percentage of corundum beads is, or the percentage of broken glass beads appears to achieve a maximum, and then it's dropping again. So that is quite typical, as expected for the softer fraction. This is something also seen by Förster now. If you have the same size and the same and just different materials. More interesting is if we use now the particles, the smaller particles, in this case 3 millimeter glass beads, and then the 1.5 millimeters glass beads. Let's just jump to the 1.5 to the smallest fraction. You can see here that even here we have a small slight increase only at the very beginning, with the first glass beads being poured into the mixture. While from that point onward, the glass beads are less and less broken. So essentially, we see that even the glass beads have, or the glass itself should have less competency, but the size of the beads is smaller, and with the size effect, the strength again becomes comparable to the corundum beads. And then all of a sudden we find essentially that the corundum here is breaking more than the glass beads. So the negative figure shows that we have a preferred comminution of the glass beads, and this is already in the case when the glass beads exceeds the 25% margin here. So we can see a very similar result looking at the limestone and quartzite comparison. We have we add 10% of limestone to the quartzite. We see that both fractions are similar broken, so we don't have much change. But then we see that the limestone breakage is reduced, and we have essentially an increased breakage of the quartzite fraction. Here we have a point where the limestone is where we repeated the test, and we could show that the repeatability of the test is quite nicely. So conclusion, influences of size strength effects of various phases on the selectivity ought to be considered, in particular in their interdependency in confined bed comminution. While in coal or cement grinding, the feed materials are comparably homogeneous, in ore grinding, influences of grain sizes, grain shapes, and strengths in the various phases have to be considered. Under certain circumstances, the softer materials can crush the harder material, and the confined bed comminution might increase the footprint in ore, and that's why we have to investigate this. Particular, the VRMs now get their foothold into the ore grinding. We see good chances there for the VRM. And of course, very clearly, we have to investigate the influence of this size and shape strength in the comminution of real ores. So far, we just used it here for different rock materials or different artificial materials. So the real ores are still pending, so we didn't check it the same test for the real ores for the moment. So that's just to show that the VRMs is not an investigation of our times, and the CPC has been, and this early type of VRM was installed many years ago already, thousands of years ago as an operation, so we don't see that's a pretty new thing. Literature, there's a wide range of literature here to be checked for the supporting, and this is about my presentation. I am welcoming your questions. Thank you very much.
Well, thanks a lot, Holger, for the great presentation there. So we're still a little bit kind of over time a bit, but I guess we can have a few questions still, just imposing a bit on people. So maybe people can volunteer in the chat if they want to put a question. But maybe in the meantime, let me just take advantage of my position here to ask you a first quick question, which is, you mentioned that in the end of the presentation, of course, there's still quite a lot of unknowns as far as understanding interactions of materials in a bed to be able to actually say that we already understand enough to be even to model it. So my question to you is that several of us here on the GCC are involved in P9, and right now this project we are dealing with multi-component simulation. And can you actually say that we're still a bit far from being able to predict what happens in a confined bed for a mixture of materials?
Yeah, I would clearly say so. I mean, particularly if you are looking about modeling and simulation. I mean, we just finished the thesis here on this type of modeling, and particular if it comes to questions here, we are talking about materials where we have a clearly defined characteristics, like or rather clearly like limestone and quartz, pretty pure actually. It's a quartzite, and so this is, it's pretty simple. If you come to real ores, even in the grains, you have the grain. I mean, I mentioned already the grain size, which could have an influence. You have varying grain size in the material. We are just looking at the slacks. I'm quite curious in the outcome of our slack investigations, because also there the grain size distribution is quite wide for the manganese material. And then you have, next to the grain size, you will enter the grain characteristics, and there is, particularly in the Russian literature of the 1960s, you find still a lot of characterizations, and they spend quite a bit of time on investigating the minerals, the pure mineral characteristics. But then, particularly, you have your mineral boundaries, and you have, for geological reasons, you have your alterations close to the grain boundaries. This all has influences on the breakage characteristics. For a granite, we just did it, or we tried a comparison in the or a re-engineering, I would call it, We did some experimental tests, and then we used, I think, quite a good DEM model, or geometrically quite good DEM model. And we developed a so-called grain boundary factor, which was just a figure reducing the strength and comparing to the adjacent minerals. And the grain boundary, we found that a grain boundary factor of about 80%, 82%. We pretty much hit the results of our experiments. But of course, this is just a very rough idea. It's coming closer to what has been seen before, but we are still far away from really determining in the mineral, or having a good test to determine the mineral characteristics in itself. And then starting from that point, starting modeling and calibrating our DM models, for instance. Yeah.
Okay, thanks a lot, Holger, for the answer. Tony already posed the question. Tony, should you ask it, or should I? Please go ahead.
Thank you. Thank Holger, very good presentation. I just want to know, because you mentioned this compressive type of particle size distribution, they would have a limit in terms of the fineness target. I would like you to comment on that in terms of the VRM, number one, and then number two, what do you think the dynamics of a flotation concentrate made up of quartz and pyrite, as in the pyrite would you expect a similar kind of challenges with the quartzite limestone that you illustrated? Thank you.
I'm not quite sure whether I caught your question correctly, but for sure you would have in the flotation you see, or if you crush a material or grind a material down, you have to go first to see the liberation size, the liberation particle size, and you have to grind it down. And the question is always then, of course, if you have a confined particle bed, whether you achieve a selective comminution there. I would be cautious, because you have to have a very thin particle layer there. And I think without shear loads, it might be difficult to achieve a liberation size of less than 45-50 microns. So that's why I would expect you need to do something there. With regard to the flotation, there have been quite a number of publications which indicated that you have an improved flotation. I think in 10 publications roundabout which we investigated, I think 8 of 10 were describing better flotation results, and 2 were describing a reduced recovery in flotation using this dry comminution. But in general, and this appears to me to be quite clear, if you don't have this slurries where the particles are floating in, then you don't spoil the surfaces, and the flotation might certainly improve.
Thank you.
Yeah.
Okay, thanks, Holger. Thanks, Tony. There's Vlad who wants to make a question.
Thanks, Holger, for great presentation. Just a question. You showed the results that VRM when you broke the material using VRM, the liberation was much better. You achieved higher liberation at a coarser grind size. And correct me if I'm wrong, but those VRMs were close with the dry classifier. Am I right?
Yeah.
And is there any? What do you think? Was there any influence, either positive or negative, of that grind classifier on that liberation results?
Yeah, I would say I would not say, and if it came around this way, I would not say the HPGR or the VRM is better or not. I think both machines have their application in confined bed comminution, and the HPGR is already well in place in the industry. The dry classification has, or in VRMs at the moment, the dry classification is the only way to go. And this is, on the other side, is certainly also a limit, because if you have a wet ore, and in many cases the material is humid, and talking about wet ore, I speak about humidity of more than 4%, which is not really, you don't have water flushing out. So with 4%, you would have to dry the ore before you go to VRM, at least at the present technologies. And then the whole thing is not making much sense anymore. So there is clear differences. I think the HPGR with regard to humid material, the HPGR has at least to the present state of knowledge, it has advantages because you may use at least rather dry material or rather wet material, depending on the way you look around. There's publications how the efficiency of the grinding process of HPGRs is reduced by humidity. It is reduced, but still you have the chance to use material instead of a pebble grinder, to put in a pebble grinder after the segment. You might think about putting in HPGRs, which could improve the performance of the segment of the recirculated material, because you not only crush the material, you also introduce these latent cracks, which also again improves the performance of the segment afterwards. So I think in combination with segments, for instance, the HPGRs made already quite a good performance, or showed quite a good performance. And I think there is a lot of opportunities to equip segment circuits, AG or segment circuits with HPGRs to increase the performance of those circuits.
Okay, thanks a lot. Thanks, Holger. Any other question? Yeah, this is definitely a topic. It's really a hot topic for research and application. I'm quite sure within the next few months we'll have new seminars on the general topic of confined bed comminution being presented here in this forum, because I think it might be I could be wrong, but it's maybe the topic that really puts us all together on the GCC, because I think we have work going on in every single center in different aspects of it. So very nice foot into this topic by Holger. It will certainly be a topic that will come back over and over in different aspects in the upcoming seminars. So if anyone else wants to
I have a short question to Holger.
Please.
So thank you, Holger, for a very interesting presentation. I'm just wondering about the speed difference for the VRMs with the conical rollers. What is the range for the speed difference in percentage, or just to understand the shear component?
Yeah, it's difficult to say. I think it depends pretty much on the conus angle of the rollers, which could be everything between 0, which would mean a cylindrical roll, and it could be whatever 30 centimeters, and then it depends on the thickness of your roll. Then you have the diameter, or the difference in diameter, and you can calculate it with the speed. And so I would say it's in the range of 10–15% or something like this.
Okay.
Just assuming, depending on the width of the rollers, and there's a few factors, but essentially I would say it's typically is in that range. So if you have ground rollers, then again the picture might be quite different. So you have this FS Smith rollers with the double tired rollers and everything, so which is also quite nice for cement grinding. Not so applicable, I think, for the minerals.
Is there any good measuring method to measure the shear component? Would that be a shear box, or if you would go to the laboratory and measure that influence?
No, we have not. I would have to think about it. We didn't do it here. What we did is some investigations on the particle size distributions in the particle bed itself, of the vertical roller mills, which also gave some quite interesting insights into what happens actually in the particle bed and the normal comminution process. But putting a shear cell in, you have to. I would have to think about it.
I haven't seen so many examples of that. I've read about it, but I never seen it in real life, and I'm just assuming it's quite complicated. But
yeah.
Okay, thank you.
We soon get a VRM here running in our lab, so then I might think about it, whether we find something.
Okay, thanks, Magnus, Holger. So, any other question? So if not, I think we can definitely, we went 15 minutes overboard, and I think it's been a fantastic presentation to kick off this big area, as I mentioned before, of confined bed comminution. A lot of activity going on right now within our groups. Looking forward to look at the upcoming seminars, but definitely great contribution for Holger. Thanks a lot. I'm looking theory to practice. And if there's no other questions, I guess we can be closing and invite you already to the 27th of August to our new seminar. It's still to be defined. Anyone? Is still a question or not? But the 27th, there's going to be another seminars that you'll be invited to in the week or two. Yeah. So if not, I think we can just thank Holger again, and
yeah, thank you very much.
Virtual applause there to him. Thanks. Great.
Okay. Thank you very much.
Thanks everyone for coming as well.
Yeah. Thank you for listening. Thank you for your time.
Cheers. Bye.
Cheers.
Thank you. Cheers.